All right, guys, welcome back for part 2 on our lesson on factoring quadratic equations when there is no common factor and they factor out into a pair of binomials. So there's a few special cases that you'll want to be aware of as you're going into expanding and factoring. And one of those cases is the case of a perfect square. So in order to show you how it's special, we're going to first start by expanding one, and then we'll look for some patterns when it comes to factoring them. So here's a perfect square binomial. X plus 3 quantity squared means you're going to take x plus 3 times itself. So let's go ahead and grab a whiteboard tool and see if this works this time. This expression is x plus 3, I can draw pluses, times x plus 3. See how that is? That whole expression is squared, not x squared, not 3 squared. Now there's a wrong way to do this. The wrong way to do x plus 3 squared is to do x squared plus 3 times 3, which is 9. This is not correct. Okay, so you don't just square the first term and then square the second term and call it done. No, 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 that's wrong. So what you should do instead is you can use FOIL to expand it. But once you expand it once with FOIL, you'll see that there's a pattern that you can use in the future. So first we'll do the first terms, x times x, which is x squared, and then 3 times x, which are your outside terms, so that's 3x. And then your inside term is another 3x, so we'll add another one of those on. Sorry, I'm crowding things a little bit here. And then your last two numbers are 3 times 3, so that's 9. Combine your like terms and you get x squared plus 6x plus 9. So before we talked about how there's this pattern where this middle term is what you get when you add the two, these two last terms together, and then the end term is what you get when you multiply them. When you have a perfect square binomial, this is 2 times that number, so like 2b, and then this one is b times b, so b squared. And the final binomial will be x plus b. So look for any kind of pattern where you see this number is twice something, and then the last term is that something squared, and then in that case you have a perfect square trinomial. So let's take a look at it with a few examples here. For this one here, x squared plus 10x plus 25. I think I see a pattern here where this one is 2 times 5, and this number is 5 times 5. So that's twice a number, and that is that number squared. This one factors out to x plus 5 quantity squared. And if you expand it using FOIL, x plus 5 times x plus 5, you can see it expands out to that exact same thing. In this example, x squared minus 14x plus 49. So this is 2 times negative 7, and this is negative 7 times negative 7, so it's negative 7 squared. Therefore, this one factors out to x minus 7 quantity squared. So look for that. If that middle term is negative, that's a good hint that that's a negative term right there. So try the next few on your own. You should see a real similar pattern. Look for something where the middle term is twice a number and the last term is a number squared, and then you've got your factoring all set for you. It's a perfect square binomial. So on to the next examples. I'm going to erase this. Another type of pattern that you really need to look for is a difference of squares. So let's look at this example with expanding this special binomial, x minus 5 times x plus 5. When you expand binomials that have a pattern like this, x minus a number times x plus a number, you get a really cool result. So watch what happens when you expand it. X times x is x squared. X times 5, that's the outside terms, is 5x. X times minus 5 is minus 5x, and then negative 5 times 5 is minus 25. That's a negative times a positive, so it comes out to be a negative. when I combine my like terms, I get x squared, and then the plus 5x and the minus 5x add up to 0. So that middle term kind of goes away. It's not there anymore. But we still have the minus 25. So in this special case, we have x squared minus a number, and the middle term is completely gone. And the way to factor something like this is to recognize this is a difference of squares. This first term is squared, and this last term is a square. So therefore, when it factors out, it factors into x minus 5, the square root of that last number. Oh, I had a drawing problem there. X minus 5 times x plus 5. So sort of a neat little special case there. And you can find that in these examples here. So x squared minus 64. The square root of this is x, and the square root of 64 is 8. So therefore, this factors out to x minus 8 times x plus 8. Okay, so you just take the square root of that and the square root of that, and then one term is minus and one term is plus, and that's how that factors out. It's kind of cool. I do want to show you one special case with these, and that would be an example like this, x squared minus 6. So in this case, you still have a difference of squares because you don't have a middle term. There's no plain x in it, but this is a perfect square. 6 is not a perfect square. 6, there's no number that you can multiply by itself, no rational number you can multiply by itself to get 6. But you can still factor this. The factored expression just looks really weird. This would be x minus the square root of 6 times x plus the square root of 6. Because the square root of 6 times the square root of 6 is 6. So you just take the square root of that number, and it's x minus that times x plus that, and that's how that factors out. Funky little special case, but I sort of like puzzles like that. They're interesting. Lastly, I'm going to show you one other special type of trinomial you might run into, and that is the trinomials that have a common factor that you can factor out first. So one example is this one here. This is a tough one for me to know how to factor because I'm not very proficient on my multiples of 162, and there's also this weird 2 in front of the x, which makes factoring a little trickier. However, I might notice that the 2 is a common factor of all of these numbers. 2x squared can be divided evenly by 2. 36 is an even number that can be divided by 2. 162 is an even number, so we know it must be divisible by 2. So let's factor out 2 from the whole thing. So 2 times, and then we'll write down what's left when we divide out the 2. 2x squared divided by 2 is just x squared. 36x divided by 2 is 18x. And then 162 divided by 2 is, I think, 81. And now the rest of this term, this looks factorable. And not only does it look factorable, 18 is twice a number, and 81 is that number squared. Can you think of what that number is? It is 9. Very good. So 2 times x plus 9 quantity squared. And that's the final fully factored form of that trinomial. Let's try the next one. 4x squared minus 36x plus 72. This 4 in front of the x squared is going to really mess up my factoring, so let's divide it out. And if I do a quick inspection, I see that these numbers are divisible by 4. You can do 36 divided by 4, and you can do 72 divided by 4. So if we do that first, it might make our work a little easier. 4 goes on the outside, and then we'll do 4x squared divided by 4 is just x squared. We'll do a minus there. 36x divided by 4 is 9x. And I know 72 is divisible by 4, but I forget what that is. Let me find out real quick. Oh, I can't see my calculator because of the drawing tools. So it's 18. There we go. And now I'm going to look for a way that I can factor this a little bit more. So this does not look like a perfect square, but I'm trying to think of two numbers that if I multiply them, I get 18, and if I add them, I get negative 9. So since this is negative, that suggests to me that both of the factors are negative, and a negative times a negative is a positive. So let's play around with that. 18 could be negative 9 times negative 2. I'm getting a little lag in my drawing again. But negative 9 plus negative 2 do not equal negative 9, so it's not that. It could be negative 6 and negative 3. And that one looks promising because negative 6 times negative 3 is positive 18, and negative 6 plus negative 3 is negative 9. So I think that is my factored form. It's 4 times x minus 6 times x minus 3. And I'm writing real slow so the lag doesn't catch up to me, but that's the final factored form of that expression. In your Khan Academy practice that I've linked to from here, it guides you through some example problems that you'll factor using that common factor method. So give those a try and see how it treats you. And thanks so much for following along here. I know this stuff starts to get really tricky, but again, the biggest thing you can do to really help yourself out is know your multiplication facts inside and out. So practice them a little bit every day. Okay? And I hope you have an awesome day, and I'll see you tomorrow.